All right, so my talk here today is on, it's on concurrency in general in servers. I'm focusing on web servers, but most of what I'm talking about with regard to web servers can be applied to any kind of server you might be interested in writing. A little bit about myself. I've been doing Ruby since 2001. I think the first version I installed was 1.68. And I've been doing web applications specifically in Ruby since 2002. And since that time, I've done countless sites, apps, servers, etc. Worked with Engine Yards since 2008, and as Jonan mentioned, I'm the former 186 maintainer, and the last time I was at RubyKaigi was in 2011 when I announced the end of life of 186. So in talking about web servers, just sort of to preface all this, just a web server is nothing special. It's just a server that deals in HTTP. It accepts HTTP requests and it returns HTTP responses. Nothing fancy going on there. Now this little snippet of code, though, I thought was kind of interesting. It comes from one of CERN's first web pages where it's talking about web servers. Well, not this specific one, because Ruby didn't exist then, but I modified it to use Ruby instead of Perl. And that, in combination with a little bit of Netcat, actually is a working web server. You can run that and you can access static files using your web browser with it. It's kind of frightening, but I thought it was kind of cool. And on that same page, there was this quote, which just made me smile, because if that isn't an endorsement for us writing web servers in Ruby, I don't know what is. So when we're talking about web servers, again, there's nothing really special about a web server versus any other kind of server. It's just a server. Web servers typically listen on some sort of a network socket, and they accept HTTP requests, and they return responses in HTTP. And with Ruby, Ruby gives us a nice set of networking libraries that make it pretty simple to put together simple servers. The code on the right doesn't actually do much, but that is a viable server in Ruby. Now, a quick tangent. There's a one-liner in Ruby that you can run to start up a working web server. How many of you know what that is? Not very many. Well, that's it right there. That'll start a working web server in Ruby off of any standard installation. Now, it is kind of cheating, because what it's really doing is it's using the un.rb library, which encapsulates a whole bunch of different tools. And one of those is a command HTTP that, in turn, uses the web server that is distributed with Ruby WebRick and goes and sets it all up for you. Doesn't really have anything to do with concurrency specifically. It's just one of those things about Ruby and its web server support that I thought was kind of interesting, so I thought I'd throw it out there, because I think a lot of people aren't aware that you can easily start up a web server just from the command line with Ruby. You know, what this does is it starts up a server serving your documents out of your current directory onto port 8080. So, all right, back to the main reason why I'm here, which is server architecture and concurrency with servers. All servers are going to have the same sort of setup. They're going to parse the command lines, do their configuration. They'll listen on some socket or some sockets for communications, and then they enter a loop. And in that loop, they're going to accept connections, and they're going to handle connections. And that loop is really where all of the concurrency options that affect how a server is going to perform, that's where all of that takes place. Now with Ruby, with every server that I'm going to talk about, and almost everyone that I'm aware of, the networking is handled in one of two ways. It either uses the native libraries that are in Ruby, or it utilizes a library called Event Machine, which provides a event framework for writing servers in Ruby. Now, Ruby itself has a really rich set of tools, like I mentioned, to write servers. And again, this is just a tiny little framework, but this is about all you need to do to write a basic server in Ruby. Now, as it turns out, let me reorient here. So, when we're talking about concurrency, I needed a tool or a web server that I could use that allowed me to plug in different kinds of concurrency into it while not changing anything else. If you go and you use the various different Ruby web servers that are out there and try and talk about this, it's difficult to compare performance because there's all sorts of other implementation details that vary between the different Ruby web servers. And so I put together a really simple Ruby web server called Scrawls. And Scrawls features a pluggable architecture that lets you tell it, all right, you're going to be a multi-threading server, or you're going to be a multi-processing server, you're going to be an evented server. And you can plug that in while keeping everything else the same. And so it gives me a nice tool to compare and contrast how changing out different concurrency options affects how the servers actually perform. And it also has options so that you can vary which HTTP parsers you're using. Not really utilizing that feature in this presentation, but it was inserted into it. And so Scrawls, it's up on GitHub if you want to take a look. It's fairly incomplete at this point in time, but it works for the purposes of this presentation. And I have 4 different I/O engines, which are concurrency engines that I've put together for it. One is simply a blocking single-threaded engine. Another one supports multi-processing. Third one's multi-threading, and then the fourth one supports event-based concurrencies. All right, so the first thing we'll talk about, because it's the simplest one, and it's kind of the foundation for everything, is a simple single-threaded blocking server. This is the most basic unit that you can deal with when you're talking about a server. And again, that same code that has popped up several times there to the right is an example of this. All that does is it creates a server, and then it enters a loop, the main loop that I mentioned earlier. And in that loop, it accepts a connection from the kernel, and then it passes that off to another method that handles it. Whenever it's off handling whatever it's going to do in that method, this server can't respond to another connection. If there are a bunch of connections that come in, they're all going to sit there, and the kernel's going to have to queue them up and wait for this server to get done handling whatever it's doing so that it can come back up in that loop and it can accept a new connection. So let's try a few things. For all of my tests that I did, I ran them on a 8-core VM that was running Ubuntu 16.4, and I ran all the examples with Ruby 2.3.1. I used Apache Bench as my benchmarking tool. There are a number of different benchmarking tools out there. There's HTTP perf, that's another common one. Pros and cons of them all. I use Apache Bench just because it's quick and simple and readily accessible. It's easy to understand what it's doing. So for the first example here, we run Scrawls with the single threading I/O engine. This implements a single thread of execution in a single process, and whatever that thread is handling a request, nothing else can be handled. I set this up, and then I ran 100,000 requests against it, running them one at a time, a concurrency of one. And the test.txt file that was used there is about 1K long, just a plain text file. And so as you can see on that particular server, it really wasn't that slow. 3,614 requests a second, that's not too bad. But the devil's in the details. This is a relatively small file, it's just a text file. And because we were running the benchmarking locally, you can see when I ran it, I just ran it against the loop back there. So because we're running the benchmarking locally, network latencies don't really exist for purposes of the requests. So we were just really testing the throughput of the server itself without introducing any sort of real-world slowness. And in reality, the real world is slow. When we're doing web server things, when we're building web pages inside servers, there's all kinds of things that can be happening. You can be querying databases, interacting with other microservices, iteratively generating content from things that you've extracted elsewhere. All that assembly takes time, and then we're dealing with real-world networks. You may be dealing with a server that's sitting in New York City, and you're over here in Japan. It takes a while for all those bits to fly back and forth across the world. And that affects how servers actually function. It slows things down a great deal. And if we look at that single-threaded example, in that context, it will change a great deal. So what I did is I created a very simple little rack app. Scrawls has really, really basic rack support, but it was sufficient for this. And that rack app, all it really does is sit there and waits for 1 second before it lets the app finish and return a response. And so when I do that on this single-threaded blocking server, our performance falls predictably to 1 request a second. Makes it far less useful for doing real-world work. And that's the problem that you run into with single threading. This is what it looks like. You're standing in line, waiting for that one cashier to take care of you before the next person can go through. Concurrency is how we address this problem. And there are 3 basic approaches to that: multiprocessing, multi-threading, and event-based concurrency. So when we talk about concurrency, the book definition is decomposing a problem into order-independent or partially ordered units. We're taking a problem and we're breaking it down into smaller bits that can run independently or mostly independently of each other without any concern over which happens first. Now, when we're talking about concurrency in conjunction with performance, we usually want those independent bits to, as much as possible, happen at the same time, parallelism, along with the concurrency. And for this talk, I'm sort of lumping the 2 together, parallelism and concurrency. The more parallel we are, the more benefit we're getting from our concurrency. So for the first option for dealing with performance and concurrency, we'll look at multiprocessing. Multiprocessing is just exactly what it says. It's instead of having a single process, we have multiple processes. And we have some entity that will load balance the requests to each of these individual servers and make sure that the responses get back out to the right client. It's a very simple way to go. Easy to implement. The performance can be pretty good as long as you have sufficient resources. The drawbacks of it are that managing your processes can be kind of complicated. If you tune your deployment for a certain level of load and then you find that you don't have enough resources, well, you've got to deal with creating more processes. If you run out of resources, because processes can be kind of heavyweight, you have management complexities there. And because processes are heavyweight units, and each process has limited sharing with other processes of its resources, if you have a lot of processes, it can get kind of expensive on your resources. And those are kind of the negatives. But they're very simple to implement. In a simple server like the code that I was showing, it's pretty much as simple as this. You just go through and do a whole bunch of forks. Detach those from the parents so that you don't have any signaling issues. And there are some Ruby libraries that will do this a little bit more cleanly and a little bit more completely, but this is sort of the distillation of what it takes. It's pretty simple. Drawback that I didn't mention before, though, is that it does not work on Windows, and it doesn't work on JRuby. So if you're dealing with multiprocessing through forking, you have to do more sophisticated things in order to deal with Windows and JRuby involving spawning processes, and it's a little bit more complicated. It's a lot more complicated. But let's take a look at how it performs. And what we did here is I ran the multiprocess I/O engine, and I told it to run 8 processes since we have 8 cores on the VM that I was testing with. And then, for the first test, I just pulled the fast static file, and it's quite fast, 18,000 requests a second. Now again, that's not counting any network latencies or anything, but the server itself churned through those requests pretty quickly because what was happening is that the kernel on the server was sending all those requests to different processes and letting each process handle a subset of them. And so all the cores on the VM were able to get in on the act, and we had much more complete utilization of the resources on the server. Now things get a little bit different though when we run one of the slow requests. When we do that, you see the throughput drops down to essentially 1 per second per process that we're running. And this is because each of those separate servers are still themselves a single thread and blocking. So each of those single servers gives you the same performance profile that you saw when I showed the original single-threaded server example. We get 1 per second. But we can manage our throughput in a multiprocessing environment by just creating more processes. If 8's not fast enough and we need more, we can create more. So I created 32 and got a throughput that's almost 32 requests a second. Now, that's basically the concurrency model that you have when you go to any large store. You've got a bunch of checkout aisles, and everybody queues up in one of those lines and works your way through. Now, the drawback, as I mentioned earlier, is that it can get expensive on resources. 32 processes means 32 separate chunks of memory being used, and that can add up. And then the other thing is that if you mismanage your resource allocation so that you don't have enough processes, then you may be back in this situation where you don't have enough throughput to manage your demands. And so there's some management that has to go on when you're dealing with processes like this. Now, on the RAM utilization issue, one thing to mention is that Ruby pre-2.0 was very fork unfriendly, and multiprocessing would consume a lot of RAM. And this was because pre-2.0, the garbage collection was not copy on write friendly, whereas our modern Rubies are. And so that's a distillation of the RAM usage from the Ruby processes that I had running for that 32 process test. The column on the left is the virtual set size, and the column on the right is the resident set size. And so the column on the right is the amount of memory that is uniquely being used by each process, whereas the column on the left includes all of the shared resources between various other things. And so the column on the right, much smaller. You can run a lot of processes on this system, and you will before you start running into memory difficulties because they're sharing most of their resources. Now, I don't know how many of you know what copy on write is, and so just covering it really quickly in an abbreviated way. When a process is forked, the system makes an array basically where it keeps track of all the resources that are shared between the parent and the child. And as long as the child doesn't change any of those things, it'll keep sharing them, and it doesn't have to make a separate copy for the child. The child can share with the parent. What happens, though, is if the child changes something, then the system has to go and it has to copy all that memory and create a private copy for the child. And in pre-2.0 Rubies, the garbage collector was a simple mark and sweep. And so when it would go through all the Ruby objects to see what it needed to collect, that marking operation would change each of those objects. And the end result was that on pre-2.0 Rubies, didn't matter what happened right after you forked. As soon as the first garbage collection cycle ran, the kernel would go copy all that RAM, and suddenly you have huge processes instead of those tiny little 17 megabyte processes that you saw there for resident set size. But fortunately, hopefully all of you are using a 2.0 or later Ruby, and so you don't run into this problem. It's much more friendly to forking now. So the next type of concurrency that is commonly used is called multi-threading. Threads are the smallest sequence of instructions that can be managed independently by the scheduler. So they're smaller than a process, and multiple threads can live within one process's memory. The advantage of threads is that they're easier to manage, they're lightweight, and they can be performant. The disadvantage is that threading implementations can vary quite a bit on different implementations of Ruby. So MRI's threading is different from JRuby's. JRuby doesn't have the global interpreter lock, and MRI does, and that can make a big difference. And also, as Koichi touched upon discussed in his presentation yesterday, threading is complicated, and it's really easy to screw it up. But while not going into any more details than that, there's a few resources that I have in my slides, and if you go look at the slides later, you can take a look at these, and it'll give you a rundown on threading in Ruby. It's pretty easy to naively implement something that uses threads, and so in Scrawls, the I/O engine does something very similar to this. It just creates a new thread for each request. And as you can see, if we run the fast test on the threaded implementation, it's still pretty fast, but it's actually slower than the single-threaded one. And that's because what it's doing is it's creating a new thread for every single request, and the overhead of creating all those threads bogs it down for the very fast responses. If the multi-threading supported thread pools, which is where you have a limited set of threads and you just keep reusing those same threads over and over, it would bypass a lot of that penalty, that tax, and the fast, short test would be much faster. But still, 3,000 requests a second, that's not too shabby. Where it shines, though, is when you're dealing with the slow requests. Inside a single process, we aren't multi-processing here. We can handle, if I sent 100 requests per, at a time to the server, each of those requests waited for a second, and we got a throughput of almost 100 requests a second out of it on a single process. And this sort of performance curve tends to grow fairly linearly until you get up to very high numbers of concurrent requests. Once you get to those high numbers, your overhead of dealing with all the threads starts to give you some diminishing returns, but it's still pretty, has a pretty nice performance curve there. And that's all occurring within a single process. Now, you can mix multi-threading with multi-processing. There's no reason why you can't. And so if we go and we run the multi-threaded handler across 8 processes, that mitigates a lot of the performance penalty. It's still not as fast as the single-threaded one was, because there's still a lot of thread overhead, but we're now going 9,500 requests a second. A lot of that penalty is from the global interpreter lock. If we were able to run this test on a Ruby that didn't have that lock, you might see something different. And if we run it, the same test on one of the slow requests, well, then it really shines. I mean, we're getting 900 requests a second when we're multiplexing that across a whole bunch of processes. So that's where threading can really shine, is if you combine it with multiprocessing. Now, the next category of concurrency handling is event-driven. In Ruby, when we talk about event-driven, what we're really talking about is we're talking about something called a reactor pattern. And a reactor is something that takes asynchronous events, such as a network connection or a socket being ready, having some data to read, something being ready to write, and it handles them with synchronous callbacks. Where it shines is with I/O latencies, because most of the time a process is just sitting there waiting on something else. And so when it can go and it can interleave all these different tasks that need to be taken care of, just as they're ready to be taken care of, you can get a lot more efficiency. Now, one thing to note is that because the callbacks are synchronous, if a callback is slow, it will block the whole reactor, and so nothing else can run while that slow callback is being handled. Now, the benefits to it are that it's fast and it's very resource friendly. A single process can handle a huge number of concurrent connections, as long as you have an event notification facility that can handle that. The drawback is that slow callbacks block the reactor, and callback structured programming is really confusing. It's hard to debug. Again, there's some links if you want to read more about event-driven programming. It could be a talk by itself. So the handler for Scrawls uses something called Simple Reactor, which is just a small pure Ruby reactor implementation. And I'm going to try and move a little faster because I'm taking too long and I'm running out of time here. So dropping right into it, single evented process. It's pretty fast handling those small files again, but predictably, because again, synchronous callbacks block the reactor. If you have something slow happening inside the callback, you get slow again, just like the single-threaded reactor. The benefit to event-driven reactors, though, is that they can handle huge numbers of concurrent requests inside a single process without the overhead of a bunch of threads, which take memory, without the overhead of a bunch of processes, which take memory. It can multiplex them all within a single reactor. So this is, for this example, I just ran 2 VMs. One was an Amazon VM in Oregon, and then there was a non-Amazon VM in New York City. And ran 10,000 requests, 1,000 at a time between them. And still got very high throughput out of a single process, and that was with real-world network latencies. And this is just a quick table showing, I did a bunch of different size chunks of concurrent requests, and so as your concurrency increases, your throughput drops somewhat, but it's still pretty manageable. You can take 10,000 requests simultaneously and spin through them at 2,700 a second. That's not too bad off of a single process. Now, hybridization for event-driven systems is where, again, just like with the threaded systems, you can really squeeze out the extra performance. So this example, I took the event-driven handler for Scrawls, and I also ran it threaded. And so it was able to mitigate the delays for handling each one of those processes when there were large numbers of concurrent requests, because each of those concurrent requests was running inside a thread. So we could spin through a great deal more of them every second, because we could have multiple slow ones all running at the same time without blocking our reactor from accepting new connections. And so that, Ruby, just pure Ruby plus, running on Ruby 2.3, it's pretty fast. You can get some pretty serious throughput out of Ruby, especially when you choose the right concurrency options for your workload. I'm going to actually skip that bit. Now, I wanted to go over just a quick survey of the web servers that are commonly available in Ruby and how they're designed, what sort of concurrency options they use, because they run the gamut. There's ones that do all kinds of things. The first one I'll mention is WebRick. I mentioned it at the beginning. WebRick is pure Ruby. It uses a thread-based design, and it's part of, it's distributed with Ruby. It's been there for a long time. It's flexible. It's got a lot of features, a lot more features than I think most people realize. You kind of have to go look at the code. It's pretty interesting to read. If you're interested, you should go take a look. It's an interesting read. It's some interesting code. It's fairly well documented. The only drawback to it is that it is really remarkably slow. That same server that was running all those other things, that's its speed, returning just a basic text file. It's remarkably slow, but 450 requests a second is still pretty fast for a lot of things. It's probably fast enough for a lot of things that people need to use it for. Mongrel is mentioned just because it is the predecessor to a lot of what we have today. Mongrel was written in 2006, and it uses a C extension for parsing HTTP, which is very fast and which is still used in a lot of others, and it was thread-based. Now, when Mongrel came out, Rails wasn't particularly thread-safe, and so the actual way that it was used was multiprocessing. People would run multiple mongrels and multiprocess through them, but Mongrel itself could run multiple threads. And it was end-of-lifed a long time ago. There is a 1.2 version that there's a gem available for, a pre-release gem, so if you gem install -pre Mongrel, you can get a working Mongrel and play with it. It's completely unmaintained, but again, it's interesting code to read. Swift-Apply is one of my projects. It's event-driven via Event Machine, and it's sort of a lightweight web server combined with reverse proxy, and it's very fast and in production use. If you look at it and want to give me pull requests, I'd love that. Thin is another server that is pretty old, but it still sees quite a bit of use. It is also event-driven, and so when you're dealing with any deployments that have slow requests, you've got to have a bunch of thins running in order to multiplex those, like I showed in that example. But it's pretty fast. Goliath is sort of a niche server. It uses Event Machine as well, and it tries to unwind the complexity of event-based programs using fibers. It's fast, but it's kind of, it's not commonly used, but if you need something that's fast and event-based, but you don't want to deal with the complexity, take a look at it. Puma was written by Evan Phoenix in 2011. It's another one that was descended from Mongrel, but it was designed with concurrency in mind, specifically concurrency on Rubinius and on JRuby that is thread-based. And so it uses a thread pool and is quite fast and quite performant. If you do use Thin on any of your projects and you haven't looked at Puma, take a look. You can probably migrate to it pretty easily and have see some good benefits from it. Fusion Passenger is common in the Rails world, sees a lot of use. It integrates directly into Apache or Nginx, and the newest version also, they have their own purpose-built web server Raptor, and then Passenger itself is a multi-processing design, although the commercial version, you can also run it multi-threaded. And so it handles performance and concurrency by spinning up new processes or taking down processes as needed to try and deal with your loads. Unicorn is also very common and it's multi-processing. It's not particularly fast, but it's very stable, and it deals really well with applications that have a lot of slow requests in it. And again, with the modern copy on write Rubies, you just run a bunch of unicorns and usually you're okay. Now, rainbows and yawns are both just special versions of Unicorn. And then the last one I'll mention really quickly is Server Engine. There was an interesting talk about it given yesterday. A lot of you were probably in it, but if you weren't, you should go look up the slides if you're at all curious. It's a pretty interesting thing. And more or less, Server Engine, a lot of what I said about Unicorn applies to Server Engine, but it works on Windows and it works on JRuby, and it's a multi-process design. So, I've only got 3 minutes left, but if anybody's got any questions, hop up and fire them at me, and I've got a few t-shirts, and anybody who asks the questions, welcome to have a t-shirt. Nobody wants a t-shirt?
日本語でもいいから下手通訳してくれますからしてあげます。 T シャツ欲しくない？すごくかっこいいと思うよ。誰かもらえ。
So I need a translation box so I know what he's saying.
I said I will give you really bad translation, but then I said it incorrectly. What I said was like I will get really bad translation. Then I apologized and I said no one wants a shirt. They're probably really cool looking. And then they all just sat there staring at me.
Well, if you have any questions, come find me and I'll give you a t-shirt.
また後で
Thank you.
質問があったら聞いてください。
Oh,
どうも。
there's a question.
So if copyright is efficient on Ruby 2.x, I didn't see the benefit with multi-threaded version with server compared to multi-processed version. Can you explain it again, please?
I'm not sure I quite followed you.
Because if copyright fork is already efficient with Ruby, recent versions of Ruby, I think multi-process implementation is simpler and quite efficient.
It is, in a lot of times, multiprocessing is simpler because you don't have to deal with the complexities and threading of all the shared resources and that sort of thing. Now, you still do have more overhead. I mean, each one of those processes in my test was using 17 megabytes of RAM, whereas a thread is going to use a tiny fraction of that. And so if you have 1,000 threads in your Ruby process, Ruby will handle it, the system will handle it, no big deal. But if you have 1,000 processes running, that's an awful lot of processes. And so there is a breakpoint at some point where multi-threading gives you advantages that you can't get from multiprocessing. Most of the time in the real world, multiprocessing does okay, which is why so many people run Passenger and seem to be fine.
Thank you.
And Want a shirt?
Yep. I think it later.
Yep.
I think we're out of time, Kirk.
I think we are. We've got 5 seconds left.
それでもう時間なくなりました。
Thank you.
質問があったら後で聞いてください。どうもありがとうございました。